Alright, so there we go. Finally, it's time to explain this equation a bit better. In the main video, I wanted it to be a bit more cinematic. That's why I was doing it from memory, using animations. And because of that limited me pretty severely, and I got lost a couple of times. So here we go, this time with a whiteboard, as you can see. So we start with psi. So there we go. You already know what psi is. Psi is the wave function. So it is it's actually really hard to describe. It has something to do with waves. It would genuinely take me an extra hour just to explain why it has something to do with waves. It's a very difficult thing to describe because you're basically treating particles as waves oscillating. It's complex, it's really fun, but it's not something I can explain really quickly in this explanation. So that's it. Wave function has something to do with waves, as the name would suggest. And it returns a complex number, which means a real number and a complex number and an imaginary number. The way it works is obvious. A is just a real number, so like a 1 or a 2 or a 3 or a 4 or a 5, and then I is a complex number. I is equal to -1, square root of -1, right? That's why it's an imaginary number, because if you think about it, there's no real number that you can square and get -1, obviously. That's why it's an imaginary number. It's weird, it's bizarre, it's crazy, it's not real, it's fake, right? Mathematicians are just making stuff up. And so we have this real number, this imaginary number, which we multiply by another real number to get some value. So for example, if A would be equal to, let's say, 10, right? And B would be equal to 5, then what we would get is we would get 10 plus 5i. This is just kind of magnitude, I would say, of that number, just magnitude of the imaginary number, just how imaginary it is. So we get A plus B. In quantum mechanics, the most important thing is probability. Probability of finding particle in any given space. That's why, first things first, we have to clean this up. Why? Because in probability, you can't have negative probability. And you definitely are not allowed to have imaginary probability, because that's just insane. So what we have to do is we have to turn it into a real number and a positive number. That's important. Now, the way we do it is we multiplied psi by a complex conjugate psi. Now, multiplying psi by psi would basically mean multiplying A plus IB by A plus IB. And what the complex conjugate does, it just flips the imaginary part. So flips it from positive to negative. There we go. That's what this means. Psi, complex conjugate psi, psi multiplied by the complex conjugate of psi. That's a mouthful. Basically means A plus IB multiplied by I minus IB. Simple as it could be. So now, how do we solve it? Well, if we have A plus IB multiplied by A minus IB, the way we would solve it is we would first multiply A by A, which gives us A squared. Then A minus IB, so A multiplied by minus IB gives us minus AIB. Then IB multiplied by negative IB, IB multiplied by A gives us AIB. There we go, this multiplied by this. And then the last one, which is IB multiplied by IB, which gives us negative. This is getting a bit too large. There's some shortcut for it, but I don't exactly remember. Negative IB squared. I suppose we don't need all that many. Just really often like to use the brackets here too. The I is also squared. There we go, that's what we get. Now we can clean up this equation, because negative AIB plus positive AIB just gives us 0. They cancel each other out, which means we're left with A squared plus negative IB squared. Now, what is I squared? What is I squared equal to? Well, we can just insert into the equation the definition for I, which is this. So what we end up with basically is, there we go. We end up with this. Hold on, let me just, there we go. We end up with this. That's the equation we end up with. And what's really nice about this equation is that in that equation we have a square root of -1 squared. So square root and the square cancel each other out and we end up with -1. Right, now when it comes to this equation we have two negatives, which once again cancel each other out, which means we end up with 1. And since we end up with 1, it's just 1 times b squared, or in other words, we end up with b squared. Or in other words, we end up with a positive number, because square of any real number is positive. So 2 squared is positive, 3 squared is positive, 2.5 squared is positive, -7 squared is positive, 0 squared is positive. All of these numbers squared are positive always. That's why it's so important that we end up with a positive number. So now we know that this, right, this is equal to the probability function. So we can input any given time and any given position, and we end up with probability. I suppose I should use it like, I should do it like this, because once again, I cannot stress enough just how weird it is that for some reason in quantum mechanics, in order to represent a psi function, you just use the symbol psi without the brackets. It's so weird. You can also do this if you want. I feel like this makes more sense. It makes it look more like a function. I have no idea why is that the case. I just, as a quantum physicists just like to make things complex for absolutely no reason. Just like to complicate things for absolutely no reason. But yeah, that's what we end up with. We end up with probability, which is really nice because now we can just keep on going with this. All right. So now we have this integral right here. Now, from my video, you may remember that the area under the function in probability, when you have a probability density, area under the function gives you probability in between point A and point B. So from A to B, this gives you the probability of finding the point in between point A and point B. So if you have a function, select point B, point A, point B, then this gives you the probability of finding this particle in between these 2 points. Now, what happens if we turn point A into -infinity and point B into +infinity? Well, then what this gives you is the probability of finding the point in general, from -infinity to +infinity, which means this just gives you the probability of finding the point. That's it, period. That's what it gives you. It just gives you the probability of finding the particle, which should be equal to 1. And that's one of the interesting things, which I didn't mention in the video because it would just be too long and too annoying to explain. Let me just show you my paper note thing called Space, Life and Time real quick. Over there I have this example right here for how do you normalize an equation. Why? Because when it comes to this right here, this always has to be equal to 1. The probability of, because what this basically tells you is the probability of finding a particle in general, right? If you just kept on looking forever, then you eventually do find a particle. If you don't find a particle, that means the particle doesn't exist. The particle is somewhere. We know that the particle is somewhere because it exists. And because of that, it always has to be equal to 1. It can't be equal to 0.5 because that would mean that there's a 50% chance that the particle doesn't exist. That's not how the uncertainty principle works. No, the particle definitely does exist. It can't be a 2 because there is no such thing as a 200% chance. All right? That's impossible. You can't have just like 200% chance of finding a particle. That's ridiculous. That's why it has to be a 1, always has to be a 1. And in order to make sure that it's a 1, we really often normalize the equation. Here we can see a very lovely example, isn't it? It's just it's very lovely. Yeah, there's a lot of characters in there, but by itself it's not that difficult. Once again, it's complex, not tough. So this is basically an example of how if psi, basically what we do is we add an a on the very beginning, then we solve the equation, and then we end up with a result like this, because as I mentioned, it has to be equal to 1. And so basically we try to solve for a. What a would have to be equal to in order for us to get a 1. And over here in this case, I know it's very complex, there's a lot of things going on, but if you do take a closer look, you will realize it's all not that hard. We have powers, right? We have division, we have subtraction, we have addition. That's it, no complex operations. Yes, technically there's an integral, but this is not really, and okay, this integral, this is baby mode integral. So we don't have to worry about the integral. From this point on, if you were to actually take a closer look at the equation, you will figure it out. I know there's crazy lot of things going on, but once again, it's complex, not tough. That's it, it's complex. And so basically that's what we do. So we add to the psi function, we add a, and then we solve for that a, and this gives us a value which we can use in order to normalize the equation to make sure that we always end up with a 1 right here, because it's important. You always have some probability of finding the particle. Now what we do next is something that I didn't mention in the video to the very end, and that's the expected value. When you add x to the mix right here, what you get is the expected position. Wait, not hard, because it's not an operator. That's what you get. You get an expected position of the particle, which means that well, it's actually, it's real, it's difficult to explain. I mean, okay, I feel like the name is descriptive enough, right? It's the expected position. Once again, we're working with probability. You're not gonna get the exact position, you're gonna get the expected position. So the position that you expect the particle to be in. That's this is just a formula for it. So when you have a probability function, then this is just the formula for expected value, px. So for example, if you have the probability, if you go back to the basketball example from the video, then if you were to take the function that we created, take an integral of x and this function, then you would get the expected you would get the expected value from it. So you would get the once again, it's very annoying to explain probability, man. Normally it's I'm really used to working with animation, so right now I could just put an animation on the screen explaining exactly what it does, but it would take too much time for this very simple, coherent explanation. So that's it, that is a formula. So I know it looks weird, but that's because it's a formula, okay? This is a formula for the expected value. What's next? Well, next is this. I do believe this is the easiest part of the equation, because over here we just add derivative, and since this is the quantum mechanical equivalent of position, then what we're basically doing is we're taking position in relation to time, which is velocity, and that's what we end up with. We end up with velocity. There's a hat up there, and there is a pretty cool reason for it. In quantum mechanics, hats are used. It is literally called a hat. It's a hat. It's very festive, I know. Hats are operators. So, for example, if you want to get velocity from something, then you use operators. Operators which look like this v, for example, this operator of the expected. I have heard from some quantum physicists that you're not supposed to use operators with expected. You're supposed to just do it like this. But also I heard from some other quantum physicists, well, not okay, I heard it from people that work with quantum physics that this is the operator of expected velocity, and there's a difference between, you know, operator of velocity and expected velocity. I am not 100% certain if that's the case. That's the way I've been doing it, but just in case I'm wrong, let's do it this way. So we have the operator, and what this operator basically means is that we take this, and the way this operator works is that you take the operator and you put a function next to it. So in this case, if you want to get velocity, right, in quantum mechanics, you would note it down as such. So you operate the velocity operator on psi. And what it does is basically it takes in this formula and then inserts psi into these spots. Or, for example, let's say if you have a function like lambda if you have a function like theta, all right? It's a Greek alphabet, all right? I struggle with numbers. There's too many of them. The Greek alphabet is too much. Let's say you have a function f of x, okay? Because I feel like that's a much simpler kind of notation. You have function f of x, and then after you apply the velocity operator to it, it would be equal to this, like so. That's what it would be equal to. Alright, so that's what operators do. When you have a symbol with a hat, that means you put a function next to it, and then you get something like this. It's actually, this is a pretty good way to describe it. Operators are just functions for functions. So we know how functions basically take in a value and return a value. So for example, f of x, right? So for example, f of x will take value x and return value y. Takes an x, returns y. So for example, it can take in 0.5 and it can return a 3. There we go. That's what functions do. When it comes to operators, right, so we have inputs x, outputs y. When it comes to operators, they work on functions. So let's say we have an operator u, right? So now operator u, if you operate this operator u on f of x, then what it returns you is it returns you another function. So for example, for this random operator u, yeah, I'm using u as a random operator. We don't know exactly what kind of operator this is. I don't have an example ready. Let's say we operate x squared on it, right? The function like this, and we can get in return 2x. Yeah, and that's the operator. And then this operator u for then this operator u would be then equal to the x of, and then that's what the operator would be equal to. So how in the same way that functions operate on values, operators operate on functions. It's once again quite a mouthful. So there we go, that's what operators are. That's why there's a hat in the equation. And one last thing before we part our ways, because I feel like some people would be still curious about this. I haven't done it in a while, so you know, this is gonna be scary. I'll probably screw it up in some way, but this is the actual step-by-step of how to solve this equation. For anyone who's curious, this is the actual step-by-step on how to do it. I know, it's once again, it's a lot, but I'll try to go step-by-step solve it. I haven't done, okay, the last time I actually solved this equation was, I think, 5 months ago, so it's gonna be fun. We start with this. I will use it as a cheat sheet, because obviously I don't know it from by heart. We start with this, right? The equation we're all familiar with. Once again, as I mentioned, you can add in x and t if you want. Most people don't do it. I used to do it, but now I don't do it because it just makes the equation shorter, and if no one does it, then might as well. Then what we do, in the second step already, we end up with something like this. Now this is weird, isn't it? It seems weird, but it stems from a different property of, let me just find the exact, there we go. Yeah, I'm gonna use my paper as a cheat sheet. I'm not, people on the internet really often like to pretend that, you know, they're just omniscient, omnipotent, and all the others, where they know everything. I don't know everything. I also really often need to take notes and stuff like this. So don't be scared to say, I don't know, all right? I mean, come on, as if I'm gonna memorize this, all right? Yeah. So, right here, I'm just gonna read it for the video. I have no idea what is equal to. Yeah, so we're requiring all wave functions have to be square integral. The integral from -infinity to infinity of wave function squared has to be finite or not was yes. So what this basically means is that the function can't just keep on going up, which makes sense. So for example, a function describing the probability, the psi function, right, the wave function, it can be equal to something like e to the power of was -x squared. It can be equal to something like this, right, if you want, because it's called square integral, but it can't be equal to something like x squared. because then just shoots off to infinity as you go on. Or it also can't be equal to something like x, because once again it just shoots off to infinity and it's never going back down. It makes sense if you think about it, because then kind of normalizing the function would be absolutely ridiculous process. So yeah, obviously the probability can't just keep on going up forever. It has to be finite. You have to be able to integrate it and then get some sort of value that's not equal to infinity. That's the requirement which all these functions obviously follow. And in fact, Schrodinger's equation must be multiplied by Schrodinger's equation multiplied by a constant is equal to Schrodinger's equation with the psi function being multiplied by a constant. For that, we'll have to go back to Schrodinger's equation, which I just realized I haven't shown in the video once. I just did a video about quantum mechanics now once showing Schrodinger's equation. That's cool. This is Schrodinger's equation. It would deserve a video of its own if you want. I don't want to make a video, but it's complex. But this is Schrodinger's equation, and you just have to trust me that it's accurate on this. It's just accurate, alright. I also don't want this video right here to be an hour long. It's already 21 minutes. Oh, goody. So let's go back quickly. So these are the two things which we need in order for the next statement to be accurate. And both of them, yes, they do make sense. This means we can multiply psi function by a constant.